Hello, everyone. Welcome to this session on SAP's AI platform and some challenges that we've had. Essentially, this is more of a talk about scaling challenges that we've had and how we've solved problems with scaling Istio. I'm Darren. This is Gerald, who will be talking with me. And not here today, if I can... Lisa and Ahmed, our colleagues from Singapore, they created the initial version of this presentation, but unfortunately couldn't be with us here in London. So Gerald and I are the European delegation here instead. So I'll do a little bit of a brief introduction to SAP and the AI Foundation, which is the platform that we use. And then we'll look deeply at these 6 different scaling challenges that we've had and how we've overcome them and the lessons we've learned. Hopefully then there's also a bit of time for Q&A at the end. So SAP, first of all, anybody here not heard of SAP? Everyone's heard of SAP. Oh, one person hasn't. Great, you'll love this next slide. Great. So as of last week, SAP is now Europe's largest company by market cap. So we're the Apple of Europe. We were founded just over 50 years ago. Our customers account for over 80% of the world's global commerce. More importantly, over 70% of the world's beer and 70% of the world's chocolate. So we're on a mission. Our cloud solutions have got over 300 million users globally, and we run across all the major hyperscalers as well as in our own data centers. So that's a major part of what comes up. So the AI Foundation, that's the part within SAP where we run all of our AI stuff. That's boiled into 3 main sections. So first of all, there's a training part, and that's where tenants, which can be internal business applications or SAP customers, they can bring their data from something like an S3 bucket. They bring their own container image, and we give them a GPU on a Kubernetes node where they can run their code, train the model, and then store it back on S3. So next after that, we have the serving part, and that's where tenants can bring these models that they've stored in an S3 bucket. They bring that with another container image, and we give them another node with another GPU, maybe a smaller one, and then they can run that model for serving, so people can then use their trained model. And then finally, we've got the generative AI piece. So that's where we give access to a whole range of different large language models, over 40 at the last count. So customers don't have to sign contracts with multiple different vendors. They can just come to SAP and use all of the models. We host some of them ourselves, and we talk to partners for others. And within that, there's also this orchestration layer where you can do prompt templating, content filtering, and so on. So it's all about providing the tools that you need to do an AI-enabled business application. So the platform runs almost entirely on open source. So we use something called Gardener, which has anyone heard of Gardener? Yes, fantastic. So Gardener is SAP's open source project for Kubernetes as a service at scale. So when I said we run on all the hyperscalers in our own data center, that's what Gardener enables us to do. So instead of using the Azure-specific Kubernetes distribution, for example, we just talk to Gardener as a user interface, and that lets us spin up clusters on all of the hyperscalers in our own data centers just with a single interface. Then, of course, we use Istio for all of our traffic management in cluster and all of our security. Argo Workflows is the engine that we use for the training side of things. Kserve provides the serving kind of side of things. And then for the large language models that we host ourselves, we use VLLM for that. So on top of that, we've also got a whole bunch of other open source services that we use for the kind of system level stuff. So logging, certificate management, DNS, and so on. And then there's the components we build ourselves, which are what's needed to make an actual business platform, multi-tenant, secure, and all of that stuff. So SAP and open source, we consume all of these open source components. We're not a company that just consumes and doesn't give back. So on the right-hand side, you can see we're members of a whole bunch of open source related foundations. On the left-hand side, there's just a small selection of the open source projects that we contribute to with commits. including the main components of the AI Foundation and things like OpenJDK, OpenUI5. There's many more. These are just the main ones that are relevant here. And to finalize the context side of things, so what I've been talking about so far, this AI Foundation, that's the kind of third slab down in here. Below that are the hyperscalers and LLM partners and everything that we talk to. Above that is this, where it says embedded AI capabilities. That's actually the SAP business applications. So in terms of what SAP does as a company, we sell business applications. That's the meat of it there. And customized AI is where external customers can bring their own AI loads. And finally, on top, we have this thing called Joule. That's basically ChatGPT for SAP. It lets people talk. We're using natural language. They can ask questions of the system, and that'll translate that into calling the underlying business services. So with that introduction, I'll now pass over to Gerald, and you can do a little bit more of a deep dive into our architecture.
Okay, thanks, Darren. Yeah, now let's come to our main course of the presentation, the challenges that we met. Let me first introduce quickly the architecture of AI Foundation. So, like Darren already introduced, we offer tenant the possibility to define workloads, and then we run the workloads, and then they can use the workloads. So tenants bring their container, we run it, and then they can use it for inference or for training. Also, what we offer is that tenants can subscribe to LLMs, either LLMs provided by hyperscalers or LLMs that SAP hosts inside. So that's here on the right, the GenAI proxy. So tenants, they send then inference requests to our GenAI proxy, and we forward them to LLMs, or they send inference requests to the workloads that they own, or they send administrative requests to our management API. So these requests, they are to set up things, to do subscriptions on hosted models, or to define the workloads, or to start and stop the workloads. And it's this management API that then configures Istio, that sets up the ingress management for the routing, the ingress traffic management for the routing, and that also sets up the authentication and the authorization so that tenants can access only what they are allowed to access. Also, these workloads on the bottom, they produce a lot of telemetry data, which is relevant for the tenants, and we give access to this data via a logging system. So we have logging systems that allows then tenants to access this telemetry data. And also these workloads, they, for example, training needs training data and wants to push the resulting model somewhere. So we also need to deal with egress and set up the egress rules for these workloads. And all of this has to be secure. So we need to do a traffic isolation and isolate data and, of course, certain regulatory requirements. Now I'm handing back to Darren to introduce the first challenge.
Okay, thanks, Gerald. So now we deep dive into the Istio part of things. So each of these challenges, you'll see the same diagram on the right-hand side that we just saw, and there's a red box that'll highlight the bit that we're talking about. So the ingress gateway, what that's doing for us is it's pre-processing the JSON web token that's embedded with every request. And in this case, it's, among other things, extracting the tenant information from that JSON web token. Now, we started off by implementing a Lua filter to extract that tenant information and inject it back into the request as a header for the other components to look at. Under very high load, we started to see a lot of latency there. So we're seeing up to 60 milliseconds latency at times, which is, translated is less than 20 requests a second. Now, for a massively multi-tenant system with hundreds, if not thousands, of requests per second coming in, that was no good at all. So we looked at WASM instead. We implemented a version of the filter in WASM. Unfortunately, we were using the TinyGo SDK to compile into WASM from Go. That ran out of support. It stopped being maintained and had some stability issues as well. So that stopped working for us. So the solution then was to use an external processor for Envoy. So Envoy lets you configure a gRPC service running somewhere else. So we could delegate all of this logic to a native Go component running as a deployment that could scale independently, and then Envoy just uses gRPC to the decoding. So what we learned from there is that Envoy filters in Lua, they're fine up to a certain point, but if you start hitting serious scale, the performance can be lacking. So after that point of scale, it's better to delegate things to an external processor that can run native code. Okay, so with that, I'll hand back to Gerald for the next challenge.
Thank you, Darren. Yeah. Now the story of the JOT token continues. The JOT tokens, after routing and some extraction in the ingress gateway, needs to be validated. And for this validation, we need a public key. And we get that via an JWKS URI. And in our case, basically each tenant can have a different JWKS URI. Our identity providers, they can basically assign for each tenant a different JWKS URI. So when we get an JOT token, we need to have a lookup which JWKS URI we can use for a given tenant. And the way we implemented this at first was using authentication and authorization policies. So basically, we had a pair of these policies for each and every tenant. And in the beginning, this worked fine, but then we got hundreds of tenants and thousands of tenants, and things started not working fine. The Istio sidecars in our services developed a huge appetite for resources. We had cases at the end of Istio sidecars of 16 gigabyte memory and 5 cores. But what was even worse is we saw a significant degradation of the latency. So what we then did is we externalized. We used the external authorization and implemented the logic in policy with OPA, with Open Policy Agent. And we also implemented a database lookup with suitable caching strategies in OPA. And with this, the problem was solved. The latency was back to normal. And the resource consumption was also, again, normal. So the lesson learned here is request authorization policies and authentication policies work fine out of the box, but if you get really many of them, then go for a different solution. The next challenge that we had is about the subscription to LLMs. So when tenants subscribe to an LLM, what we do is we give them an URL, and then they can use this URL to do the inference. This URL only contains an ID. So based on this ID, we need to figure out which model it is, which version it is, and which hyperscaler it is. And the way we did this lookup in the beginning was with virtual services. So we created for each of these subscription and virtual service, which matched with the ID and then injected the headers, which worked great in the beginning, but then it started cracking because we got thousands of virtual services and tens of thousands of virtual services. And we noticed that this time in Envoy, in the ingress gateway, there was huge resource consumption, and also the latency degraded a lot. So also here we externalized. We used external processor to do a lookup by ID to get the information about which model is meant, which model version is meant, and we inject that into the request so that GenAI proxy has all information. So this works fine. Then latency is back to normal, and the lesson learned here is that the number of virtual services really impacts directly the latency. We saw in experiments that it is a linear degradation of latency with the number of virtual services, which kind of is understandable because virtual services are routing rules. So you need to find for each request which routing rules apply, and that's basically a linear search. But in our case, since we just need to look up it's much better to do really a lookup with a database. Then the next issue is about our logging system. Our logging system is a system made up of several components. They run on several nodes usually, and as a best practice, we have MTLS between them. And naturally, we used Istio Sidecar to implement MTLS, which worked in the beginning great, but then under high load it didn't. And here we really have high load. Our workloads, they are producing about 1 terabyte of data each day. So we started to notice instability. At first, we were tuning then the components of the logging system itself. But then we also noticed that when we simply switch off MTLS, that everything works fine. So then we experimented with first native encryption protocols of our logging system. Also, we had a look at WireGuard on CNI level, which was looking promising. But since we anyway wanted to look at ambient, we tried out ambient, and that did the trick. So with ambient, by pushing the encryption down to a level 4, everything works fine. And the lesson learned here, our lesson learned here is, when you have systems with queries and very large result sets, potentially replication protocols. We also had this experience with a database system that we use for replication or native protocols. Then it's better not to use Istio Sidecar. It's better to go for ambient or WireGuard. And now I'm handing back to Darren.
Okay, so the final two challenges back to the AI machine learning piece. First of all, to do with training. So one of the things to realize here is as a secure multi-tenant application, when a user brings their container image to run on a GPU, we give them their own node to run on. So in other words, we never have pods from 2 different tenants running on the same node. So we've got pretty good isolation there. What that means, though, is that when that Kubernetes job appears, it triggers the scaling up of a new node with a GPU. Now, jobs come with a pod restart policy of never. And so we run into this race condition where Istio CNI is on the node and starting up, but also the pod from the job has landed on the node and is starting up. So when that job is trying to do things on the network, is trying to fetch some data, it can't do because Istio CNI isn't yet running. The other problem we have is that in Kubernetes, a job is only considered finished when all of the containers in that pod are completed. So if we now add an Istio proxy sidecar, we've got 2 containers. The main container that's doing the training might finish, but the Istio proxy sidecar is still running. So Kubernetes doesn't consider that job as having completed. So the initial solution we had for that, for the 2 problems there, first of all, the nodes that we use for this, we add a taint to them so that the Kubernetes job pod then can't land on that node until Istio CNI is ready. And there's actually a feature in the Istio-D operator that lets you specify that taint so that it knows to remove the taint when Istio CNI is ready. And the second point then is that when the job's finished, it knows it has to then call the quit endpoint on the Istio proxy sidecar. That means that then both containers finish and the job is completed. So it's not perfect solution, it's a little bit hacky. So where we want to end up with there, our next steps are doing one of the following 2 options. The first is if we use Istio native sidecars instead, Kubernetes native sidecars, they get started as init containers instead of main containers. So what that means then is Istio proxy is running as an init container. There's then only one actual main container running in the pod. So when that completes, it will happily consider that pod as completed, and that solves the problem. The other option there is to use Istio ambient, which gets rid of the sidecar container completely, and again, removes the problem. So the final challenge is on the serving side. It's a little bit similar. So in this case, in Kserve, it triggers an init container to download the model from the S3 bucket before the main container then starts serving that model. Now again, because we're running with an Istio proxy sidecar, that sidecar is running along with the main container. So when our init container is running, the Istio proxy sidecar isn't running, and so we can't actually talk to the internet to download our model. So the slightly hacky solution we have there initially is to exempt outgoing port 443, so that then anything can talk to SSL on the internet or HTTPS on the internet. It can download things from S3, and that works. It's not great. It's a bit of a security weakness that we have to just have this blanket rule to allow access to everything. So the solution is pretty similar to the previous challenge. If we use Kubernetes native sidecar, then we can configure that Istio proxy init container to start running before the model downloading init container. So the sidecar is running, and that gets rid of the problem. Or again, by running in ambient mode, we get rid of the sidecar completely, and that solves the problem. So that's the end of the challenges. I'm going to pass back to Gerald now just to summarize the lessons that we've learned from all of this.
Thank you, Darren. Yeah, let me quickly now summarize what the 5 lessons are that we learned. So first of all, the Istio standard configurations, they work great out of the box, but under high load, things can look differently. So it's really important to be aware what your workloads are and what scale, and then use Istio in a customized setup. Then race conditions can bite the initialization sequence of Istio together with the initialization sequence of your workloads. They can lead to unexpected behavior. So you really need to be aware of the dependencies there and potentially coordinate the sequence, for example, with taints and tolerations. Then workarounds can create debt. We bypassed certain Istio features, and that resulted in security risks and under high scale, under unexpected behavior. So our recommendation is really to prioritize Istio native solutions on the long term. And how to find them is to stay up to date. Reading the release notes, they in fact contain a lot of information about edge cases that people are in the beginning often not aware of. And then to stay future-proof, have a look at ambient and at Kubernetes native sidecars, especially if you are dealing with jobs or with high scale. That's it for today. We have 2-3 minutes for questions. Is there any question?
Okay. So I have a question. In one of your slides, I think I captured, you mentioned about, I think it's related to mutual TLS, right, for database. You mentioned about leveraging ambient to fix some of the issues you saw. Was it just for the particular workload that you moved to Z-tunnel layer for layer 4, and then the rest is still using sidecar? Could you elaborate a little bit more on that case? It's when you showed the login slides, if you remember.
Yes, I hope I can answer that because these observations, they were mostly done by our colleagues. But as a matter of fact, with these workloads where you have large result sets for queries and replication protocols, so database-like systems, there were instabilities which were not completely understandable for us. But also we got the feedback from the community that in such cases, it's known that this can lead to problems on the high load. Okay. That these workloads can lead to problems on the high load with MTLS.
Okay, thanks for that clarification.
Hey, thank you for the talk. Quick question on the traffic management challenge, if you can go back to this. So, trying to understand the use case, what was the challenge exactly, and basically trying to understand the red part.
Yeah, so we extracted an ID from the requests. The ID is all that we knew, and we needed additional information, what is behind this ID, to do some, to in this case, the name of the model, the hyperscaler, and the model version. So, and we need this information in the request for the actually processing component to process the request. And the challenge was that in the beginning, we had for each subscription, so corresponding to each ID, we had a virtual service, which then injected this meta information into the request. And since we had very, very many subscriptions, tens of thousands, we ended up with tens of thousands of virtual services.
But 1 second, like every subscription translates to what? A different model or like?
Yes, basically, yes, yeah.
So you're saying you had like thousands of models regardless of what platform it is, and then virtual service that extracts
Yes, yeah.
Okay. And then you moved into an XProc solution where the request, okay.
An alternative solution would have been that tenants specify these as parameters, but for our case, there are reasons why we just want to give an URL with one ID contained in it. Okay.
Got it.
Okay, thank you. I'm afraid we are 2 minutes. Okay.
Right. So this is a question about also traffic management, but also about the WASM plugins. So the virtual service, you've replaced the lookup by doing it in a database. But at what stage does that happen? Is that also a plugin that does the lookup, or is the lookup done differently?
It is done in the ingress gateway calls the external processor, and then the external processor does the database lookup.
And it returns the correct path for Envoy to forward to.
Then we get the parameters that we need, and they are injected as headers into the request.
Yeah, and the external processor then uses gRPC. So does that mean that it's co-located with every gateway or every Envoy instance or waypoint?
Yes. Yeah.
Ah, okay. Yeah, because we tried the same thing. We also ran into the problem of TinyGo essentially, not having much maintenance going on. So we switched to Rust, which was a little bit fresh, but it works perfectly well. But knowing that you can do the same thing with gRPC, I completely missed that was developed. That sounds like a very good improvement. And if it works for you guys, well, it must be good enough for us. Thank you.
Okay.